a mountain, but a steep decline, and had to get helicoptered out. Well, good evening, everyone. We're back together again with an amateur extra class series. We're going through the ARRL license manual, and we're on Chapter 8. We did Chapter 8. We're doing it in 2 halves. Tonight is the second half of Chapter 8. And then next week, Gary will be up for 2 weeks consecutively for antennas and feed lines. So if anybody is stumbling into our video for the first time, highly recommend you go back to the beginning and go through the sessions one at a time because they build on one another. So we're going to be continuing on here, finish section 8.2 on digital protocols and modes, and then we'll be talking about packet radio, and we'll end with TV, both analog TV and digital TV, slow scan TV as well. So we talked about radio teletype last week, and here's some images here that are quite interesting. And the first thing that you're going to notice, or if not, I'll tell you about it, you will never see mechanical teletype equipment that's this clean. Somebody completely restored this gear and put it out. It was a presentation. I think I saw it both in Orlando Hamcation and in Lawrenceville Hamfest. There, somebody put this together. And I wanted to, in case you hadn't heard, I wanted to play a little sound from an old mechanical teletype machine. I got to turn this off first.
Yeah. My first love.
What is that?
This Modulation. I got one Air Force surplus one time. It looked like this. About 200 pounds. I'm so proud of it.
So that was at the same Hamfest. So if you've never heard that before, it used to be back in the 60s and so forth, all of the news programs would have teletype machines running in the background. That was supposed to be the cool sound, I guess, for news services. Now last week, I think I mentioned some sites that were good for learning CW, if anybody wants to do that. Maybe not right away in their ham radio career, but at some point in the future. Last week, the CW Academy website was down, but it's back up again now. And the other one here is, the CW Academy was working, but the Long Island CW Club was not. But they're both up and active now. So I wanted to put those links up again if anybody wanted to pursue that. These are the things we'll be talking about in the remainder of section 8.2. Bunch of interesting technologies. Start out by commenting that the FCC regulates digital modes as if they were voice. And if you think about that, all of the digital modes are going to fit in the space of a single sideband conversation, or channel, if you want to call it that. Not really channelized, but that's why they're regulated as voice modes. You've probably heard of some of these things. D-Star, Yaesu System Fusion, Digital Voice, WinDRM, FreeDV. These are all digital modes that are available mostly on VHF and above, all regulated as voice modes. Slow scan TV, which we're going to come to later, is also regulated as an image mode because everything having to do with slow scan TV is done in the space of one sideband conversation. I think I shared this link prior. It's the Rules and Regs book that is provided by ARRL, and highly recommend that everybody have this in their shack someplace. It's just a good reference. So a little bit more detail here on how the FCC regulates these modes. The point here is that we can't have any secret agent man stuff going on here. We can't be sending codes or data that's encrypted in a manner that can't be decoded by other hams and by the FCC. The only 2 exceptions are control of model airplanes and satellite telemetry, or satellite control, because you wouldn't want somebody getting into your satellite and turning it off or crashing your model airplane. So those are the 2 exceptions. No pool questions on that though, just interesting sidelight. Now, APRS is a fascinating subject, Automatic Packet Reporting System. And it started off, there was a fellow called Bob Bruninga, I think he pronounces it, that developed this entire technology and made it popular in ham radio. The way it works, just a quick high-level overview, we've got radios that are out here that have APRS software on them, some kind of a modem, usually a 1200 baud audio frequency shift keyed modem, quite often a GPS built into the radio as well, that then can talk to other radios, can reach out to what's called a repeater gateway, and if that repeater gateway happens to be connected to the internet, all of this information can be shared across a wide area. There's some very good links here. The Wikipedia has an excellent article, lots of resources there. Now, Bob Bruninga, when he was alive, had a site called aprs.org, and that's being maintained for historical purposes because it's just a treasure trove of technical information. When Bob passed, another organization took it over, worked with his widow actually to acquire the internet properties, and is carrying it forward today. And there's a ton of YouTube videos on this technology. There's this link here, aprs.fi, where if you're wandering around out in the field and your radio is doing something called beaconing, which means every so many minutes it's sending out a signal. That signal may include your position data, usually from a GPS. It can optionally contain weather information, elevation, all kinds of interesting things. And that can go out through a repeater gateway, digi-repeater, out onto the internet. So here's a picture, aprs.fi, where you can go and see what's out there. And if you've been beaconing, sending out these little packets every 5 minutes from your radio, it will actually trace your route as you go from one location to another. Now there's 5 pool questions on APRS, so I'll have several slides talking us through this, just because, well, we want to be able to answer the questions, but also these are very useful tools for you to use in your practical ham radio activities. So there's quite a few use cases. I'll mention some in an upcoming slide. I'll be showing a radio that I'm using currently. Moving on. So here's Bob, who developed it all. Notice his call sign, APR, like is in APRS. That's pretty cool. I don't know if that's a vanity call, or I don't know which came first, the chicken or the egg, so to speak. Now, when he passed away, Jeffrey Hochberg in the Atlanta area got a group of fellows together and they were dedicated to carrying forward APRS. And I think I showed that. Yeah, here we go. So APRS.org was developed by Bob, and then Jeffrey and his friends put together the APRS Foundation, which is a continuation. So APRS is not going to pass with Bob gone. Now, it used to be that Kenwood was the premier radio for doing APRS. They had a portable and a mobile that were completely set up. They had the APRS modem built in, they had a GPS, had the capability of doing everything you needed in one box. They have since stopped doing that. I think they came out with another portable only that does APRS, but it's super expensive. It's like $800. It's unbelievable. Yaesu has stepped into the void, though, with both a mobile and a portable, and I'll be showing you my portable here in a bit. So what are some of the things we can do with APRS? Well, there's something called SMS gateways. You can do text messaging. I've played with this a little bit. There's interfaces to weather services, something called FireNet. Summits on the Air and Parks on the Air both have interfaces to the APRS system, so you can see who's where and you can spot yourself. A friend that first showed me how some of this worked for him personally it was Warren Lennon here in the area, one of our fellow VEs, said that he used this for vacation tracking. As they're going from South Carolina to Michigan, they would share the APRS FI site with their relatives, and they could monitor their progress as they drove from South Carolina to Michigan. So that was kind of unique. You don't have to be licensed to use the website. Emergency communications, they have something called tactical call signs. So you can set up, if there was a hurricane, and this has happened, set up a command center and then have designated people around the emergency area. SOTA and POTA spotting and tracking. The use case there, sometimes you'll see somebody who's scheduled an activation and they'll provide their call sign to look for them on aprs.fi, so you can see as they're driving to the trailhead where they are, how close they are. And then once they get out of their car, they'll transition over to a portable, and then you can continue to track them there. Major events, there's something called the Golden Packet event that I'll talk about a little bit more. Here's a system diagram. So here we've got cars and we've got people hiking, and they can talk amongst themselves. It's all packet, it's not voice. And here's a repeater. It's called, in this case, it's called a wide digipeater. No connection to the internet, but it allows all of these folks to chat with one another. Now, if there is a digipeater that's connected to the internet, like here, that's called an iGate. This could be an iGate if there was internet service up there for them to connect to, but in this case, the packets go up, get repeated off the top of the mountain, come down to a station that is an iGate to the internet, and that's what populates everything that we see on the mapping application. So another interesting use case, one that I haven't pursued yet but intend to, normally a mobile unit in your car has much better range than a handheld portable. But the mobile in your car can act as a digipeater, and then when you get out of the car, like if you're at if you're going to a Summits on the Air site, for example, you've got to hike a mile or two to get to the summit, your portable can use your car as a digipeater, which then can get out onto the system and perhaps get you spotted and located. So we're finally getting to the pool questions. I said there were 5 here. So this may be obvious, but let's go through it anyway. So APRS is a technology used for real-time tracking of balloons carrying amateur radio transmitters. I hadn't mentioned that as one of the use cases. Back when we had the full eclipse, what was that, a couple years ago now, there was a big propagation project. Some universities were launching weather balloons, and then they were sending data back from the balloons using APRS. We had one here in our area that was doing that. I think it was Clemson University. So there is a pool question that wants you to know about real-time tracking of balloons. APRS stations relay data via packet digi repeaters. And I kind of showed you a diagram of that. And here's another one here. Now there's a protocol called AX25. X25 you may have heard of before because it's a protocol common on the internet. AX25 is an amateur adaptation, so it's amateur X25, and it's the digital protocol used by APRS. There is a reference document here if you're into that sort of thing and want to see the technical specs. And within that technical spec, they talk about data frames. And in the standard spec, the data frames normally go out with a number because when an entity is transmitting, sometimes packets can be received out of order if they come in from different sources, different repeated sources. So that helps put the message back in the proper order. What happens with APRS, though, they use something called unnumbered information, which means they don't really care because they're not sending long text messages. We'll get to that when I talk about WinLink. So that this is just a little technical tidbit that appears in the pool. The type of packet frame used to transmit APRS beacon data is unnumbered information. By beacon data, that's just what all of these mobiles or portables are sending out in perhaps 5-minute intervals. So here we've got the balloon case, here we've got somebody out in the field. And this is just a different version of the diagram that I showed you before. It's possible to have multiple hops from one mobile to another to a digipeater and then out to the internet, and you can control how many hops you want that packet to take. Which gets us to the next slide. So there are different packet paths. So the packets are not directed to a specific station like they are on the internet, for example. There's no acknowledgement of receipt, so the mobile or the portable is just going to blindly send out this packet, and then it will be repeated until it expires. So there's something called a path code. This is one particular one. It's wide N-N. And here it is expanded out. Example, wide 3-1. What that means, if your radio is configured that way, the first number gives you the number of digipeater hops requested. All right? And then the hops remaining is over here. So if you want to configure your radio to do no more than 3 repeater hops or unit-to-unit hops, that's specified here, and then the entity that receives and repeats that will decrement that. So after it's been repeated, after it goes through 3 different repeaters, it will stop. So these packets don't continue on forever. So here's an example down here, a little bit hard to read, wide 3-1. So here we start out, digipeater 1, 2, and 3, and then it ends. So the reason that I went through all of that is because there's a pool question about it. What does wide 3-1 mean? Okay, that means 3 digipeater hops requested with 1 remaining. So in that case, we would actually be over here, but because we got 3 hops, there's 1 remaining, it'll repeat 1 more time, and then this repeater will not repeat it again. So something to absorb there. And the whole concept of these path codes is kind of complicated. I've gone to different Hamfest forums that explain some of this, and it gets a little bit complicated, but normally you just have your radio set up for one particular default, and then you just let the system take care of it from there. But if you want to understand what some of those are and be able to control them, there were 2 sites that this is actually the same site, just different links that talk about how these paths and the hops work. A bit more on applications. Okay, GPS information can show a mobile station's position during the event. You might be wondering, well, does your radio have to have a GPS embedded then? The ones that Kenwood had and the one that I'll show you that I have do happen to have a GPS embedded, but if you have a TNC, a terminal node controller, and there's a bunch of them available specifically designed for APRS, you just need audio from your receiver and a path into your transmitter, and you can have all of that happening in a box external to your radio. Same thing with GPS information. It's possible to take an external GPS designed for the purpose and embed that in the outgoing packets. So here we've got a map showing somebody's route. And then we've got something called the Appalachian Trail Golden Packet. It's just another application of this technology. It's a kind of a big program. Another one, last time I was at Hamcation in Florida, they had a frequency set up specifically for conveying information about the Hamfest, all running on APRS. So it can be set up to support an event, a bike race or a motorcycle race or a community event or an emergency event for that matter. Now the AT, or Appalachian Trail, is very interesting. It's about 2,200 miles long. It goes from Georgia to Maine, crossing 14 states. They use a frequency, a non-standard APRS frequency, so they won't interfere. APRS, by the way, the standard frequency in the United States is 144.390. So if you've got a 2-meter radio, if you tune to 144.390 and just listen, you'll hear all of the data going on. That frequency is used throughout the entire United States. Different countries have different standardized APRS frequencies. So the concept of a golden packet is that a packet that's been generated at one end of the trail, it makes it all the way through to the other. There's usually 15 to 17 stations set up along the path, and if you can make the entire path, you've achieved the golden packet. I don't know what you get for that, maybe a lollipop or something, I don't know, but here's a link that talks a little bit more about it. So these are just all different applications, things that you can do with APRS. GPS data, latitude and longitude. And then we're going to move on to some more kinds of packet. Now this is one flavor of packet radio. Now we're going to talk about some other packet modes that would be used more with WinLink. So some highlights here. Pactor was the king of the hill for quite a while. The only downside to Pactor is that it uses a proprietary modem that's really expensive. But it was the best way to get data from one site to another. Pactor has the ability to actually transmit not text messages, well, it would do that too, but it will send an email and files. You can send those items via Pactor. So Pactor was extremely popular during some of the big hurricanes. Puerto Rico, for example, they were just dying to have hams go down there if they could and support communications because everything else was down. It allows email and files to be sent. Pactor stands for Packet Teletype over Radio. Fancy techniques so it gets through. I said it was expensive. The modems are only made by one company, and $1,600 to $2,100, so it's kind of out of the reach of most hams. So what do we need to know? Pactor is a mode that can be used to transfer binary files. Pactor 4 provides the highest throughput under clear communication conditions. Now our license manual, and I believe the exams that are out there for the extra, at the time that this version of the pool came out, Pactor 4 wasn't legal in the US. Since then, the FCC has made an allowance. So some of the limitations that you see in our book that talk about a maximum of 300 baud on frequencies below 29 megahertz on HF don't apply anymore. Pactor 4 is legal. They don't ask that specifically here, but for the pool, they want you to know that Pactor 4 provides the highest throughput under clear communications conditions. Now, what has really replaced Pactor for most EMCOM, emergency communications organizations, something called VARA with WinLink. WinLink is an email system, free, you can download it. winlink.org, I believe, is the site. And then VARA is a software modem that will interface with your radio to do the transmitting and receiving necessary to talk to the WinLink software, email software, that will allow you to use your radio and computer just as if it were an email system. The good thing is it's got all of the things that you can do with Pactor, you can do with VARA and WinLink. It's about the same performance as Pactor 3. Some argue even Pactor 4. And it's really become the standard for most EMCOM organizations because it's affordable. Now, VARA has free and licensed versions. Some people think $69 is just a horrendous price to pay for something, but when you look at what a Pactor modem would cost, this becomes dirt cheap. So I have the licensed version myself, and I used this during Field Day this year. For Field Day, we were granted bonus points by the ARRL if you could send a message via WinLink to your section manager or emergency coordinator. That was worth 100 points. And then you got 10 points each for each additional WinLink message that you could send, up to 10. So I coordinated doing all of that at about 3 o'clock in the morning when things weren't very busy, and we got our 200 bonus points. So that's another application. So just as a review of some of the things we touched on, won't be all of it. Be aware that PACTOR can be used to transfer binary files on HF, which can be good because on HF we've got skip and long distances, which can be very helpful. And this one actually shouldn't have been on this slide, but we'll come to it later. Whisper, which we'll talk about, does not support keyboard-to-keyboard operation. I didn't catch that, but now you know. All right, HF Digital. There's a book out that I highly recommend. It's called Getting on the Air with HF Digital. Here's an Amazon link, and it's available for about 10 bucks on Amazon, or about $3 if you get the paper version. Now, it came out in the original edition, then the second edition, and I wasn't very impressed with either of those. The third edition, though, is I do highly recommend, as it has chapters on a lot of the stuff that we've talked about so far, WinLink, Navara, and a lot of the other digital modes that we'll be jumping into. My top recommendation, though, is to find an Elmer. If you're interested in any of these digital modes, find somebody that's doing it already and sit down with them, see how it works with them. So getting into some troubleshooting when we're dealing with digital modes. This could be APRS or something like WinLink. Transmit distortion. So here's a fairly clean signal. And here's one that I just called eek. That's nasty. So a common cause of overmodulation of audio frequency shift keying signals, which all of the stuff we've talked about has been in that category, is often excessive transmit audio levels. You know, if you've got a radio that has the modem built in, like the ones that, I promised to show you mine. Let me step over to the calculator cam. This is an example of an all-in-one radio. It's a Yaesu FT5D, and it's got the 1200 baud modem built into it, and GPS built into it, and you can set it up to send out beacon signals every so many minutes, and then you can be tracked on the system. Like I said, you don't necessarily have to have an all-in-one modem, or all-in-one radio, but then you'd have to have a separate TNC and GPS if you wanted to use those features. But virtually any HF or VHF radio is capable of running these modes with external equipment. This is just all built in. All right, so transmit distortion, that's a bad thing with an all-in-one radio that's already taken care of for you. What makes the signal look ugly, like this one down here, something called intermodulation distortion, or IMD. It's a parameter that evaluates distortion of an AFSK signal caused by excessive input audio levels. Your decoding program, whatever you're using to decode packet communications, may have an indicator on it, an IMD indicator. And what you should see is a value of -30 or less. We'll have that coming up too. For an idling PSK signal, phase shift keying, the acceptable maximum IMD should be down 30 dB or -30. That happens to be the lowest number that's offered in the pool question. I should be able to remember those. Now we're going to move on to somebody who's become a very good friend to amateur radio, Mr. Joe Taylor. Picture of him. He's a Nobel Prize laureate. Working with his team, they found the first binary pulsar. He's an astrophysicist, not a rocket scientist. He's an astrophysicist. So he had a talk in 2018, and I found that and put a link to it here. It's like an hour and 17 minutes, so it's really long, but it gives you all of the background between an amazing set of technology. And I put a note here that the signal to noise limits appear at 29 minutes and 26 seconds if you care to get into his discussion there. It's a long video, but I found it very, very interesting. These modes, particularly FT8, is just taken over ham radio by storm. Thousands and thousands of conversations per hour. In fact, in a couple hours it can be up to 1 million. I didn't put that chart in here. I used it in the general class, but it's become by far the most popular mode in ham radio. This, what I'm showing here, Joe talked about the levels that you need to be able to communicate. For single sideband, and this is reference to 2500 hertz bandwidth, which is about the size of a single sideband space, you need a signal that's about 10 dB above the noise in order to hear it. In other words, a weak SSB signal. Come down to CW, ear and brain as he called it, you can go down to -15, so actually well below the noise level. Now consider the difference between -15 and +10. That's 25 dB. So that's where you come up with the statements where people say that 1 watt of CW is worth 100 watts of sideband. It's actually more like 250 watts, but he comments in his video, this was originally, some of these modes, we used to have to do moon bounce. I've never done moon bounce, but those that did would have a pair of headphones on, very quiet listening environment. They'd be listening for repeats, and it was possible to have this big a difference. Gary has a comment, I think. No, he does not. All right, very good. So CW is much more effective at getting through, but then if you get into the specific modes within the WSJTX family, you can see that they go way, way down. JT65 was the first Earth, Moon, Earth mode. That's what it was designed for, but ham started using it on HF. The disadvantage to JT65, it wasn't at the time because it was all that was available. It would take an entire minute of transmit and an entire minute of receive, and you had to do about 3 or 4 sequences to complete a message. Since then, other modes have come up that take much less time. I'll show that to you. We've got some, like Whisper, which we'll talk about more, goes all the way down to -31. So one watt of Whisper is like thousands of watts of single sideband in terms of being able to be heard. So FT8 came out in June of 2017, and I got involved with it in about August of 2017, way back in the beginning. I was living in a neighborhood that had very high noise, and FT8, or the digital modes, was about all I could do at that time. So that was a wonderful thing for me. It's wonderful for DX if you're chasing DX entities. There's 340, I believe, right now. If you get more than 100 confirmed contacts, you can get an award called DXCC, DX Century Club, through the ARRL. I did all of that on FT8, actually. So I thought it would be helpful to put together a chart here of what's taking place. So this is a chart just talking about FT8. It takes 15 seconds transmit, then 15 seconds of receive, 15 seconds of transmit, so you're alternating back and forth. And they have standard message designators, TX1 through 5. And this is the information exchanged. It starts out with, if somebody's calling CQ and you're responding, I'll send their call, and my grid square. What it looks like. And the interpretation, I'm reaching out to you. And then we do a signal report. They'll tell me what they're hearing me, what level. I acknowledge and send a signal report. Roger, I hear you at -18. Now we're at 45 seconds. They send an acknowledgement. Roger, roger, roger. You see a lot of hams. And an email with RRR. That's where it comes from. And then we send an acknowledgement. QSO is completed. So a full FT8 sequence of events takes about 1 minute and 15 seconds if there aren't any repeats along the way. Sometimes a call, it doesn't get through, and then you just have to wait for them to resend. So you can see with these timings, it becomes very critical that your computer clock and theirs need to be within 1 second. It's a requirement for these kinds of modes. Very similar sequence of events for these other related modes. Okay, so they give us a bunch of pool questions here. And these were, most of them were new in their current pool, which has now been out for a couple of years. Because when FT8 came, or when the WSJTX family modes came out, they were new. Okay, so they thought they should include a lot of pool questions related to them, particularly because they've become so popular. So the length of an FT8 transmission cycle is 15 seconds. We saw that in the chart that I had up a moment ago. Synchronization of computer clocks is what synchronizes the transmit-receive timing. That's why you have to be within 1 second. And there's software that you can install on your computer that will synchronize you to a standard that will keep your time in sync. And there's several modes. They've listed some here. So of the modes that they've listed here, they want to know which one has the smallest bandwidth. So when you see the question that has all of these different modes on it, the answer that they're looking for is FT8, which is 50 hertz. We've talked about some of these before. PACTOR takes about the space of a sideband channel. Now there's a couple of modes that are relatively new. They're the newest ones in the family. Q65 is one of them. And it's kind of an amazing mode because it's designed for Earth, Moon, Earth. It's designed so that Doppler shift, in other words, if you're working satellites, it can handle the Doppler shift that occurs there. It's also used with scatter propagation. Its downside is that it can take a very long time to transmit and receive because it averages multiple cycles. In fact, it can be doing this over a period of as much as 1,800 seconds, which is 30 minutes. So at any rate, let's just take a peek here. We've talked about all of these things. T8 is the narrowest. Okay, in Q65, its claim to fame is that multiple receive cycles are averaged.
And I want to highlight something that you taught me that
Okay.
I never knew.
All right.
Is there's a website that you can go to in any browser. Just type time.is. S. Time is. Time.is. And it'll tell you what your computer clock is to a reference.
Yep.
If you're on time, then it'll tell you you're synchronized.
Yep.
If you're not, then there's something you need to deal with.
Yep. I'm glad you mentioned that. It's something that I have as a link in my browser when I'm running FT8 time.is. You know, that's a good tool to have because you can tell if you're on or off. Some more characteristics. Usually the number in these modes indicates the number of tones that are included in the mode. Talking audio frequency shift keying, the number of unique tones in that particular mode. So the 4 in FT4 refers to 4 tone, and then some fancy words here. But remember that FT4 and 4 tone is what to look for. Continuous phase frequency shift keying. Now, I said that the timing was 15 seconds with FT8. With FT4, it's half that. It's 7.5 seconds. FT4 was really more designed for contesting because you could make more contacts. It's a little bit less sensitive than FT8, but normally you only are working with strong signals in contesting anyway. Now, FST4, this is one of the newer modes. Bunch of fancy words here, and it looks like we're going to have an all of these answer coming up. 4-tone Gaussian frequency shift keying. Well, what in the world is that? You don't really need to know, but you can Google on it and learn a lot more. It's very useful for detecting weak signals. Variable transmit receive periods from just a few seconds all the way up to 30 minutes. And there's 7 different tone spacings. So FST4 is like the best of the best. but it can take forever. It's a very specialized mode, something that you probably wouldn't normally use. JT65, okay, this was the very first mode that came out in the WSJTX family. It was designed for moon bounce, and it uses multi-tone audio frequency shift keying, the FSK, and it uses 64 tones plus a synchronizing tone. And it's doing all of that within just a few hertz. We saw that FT8 only consumed 50 hertz. I don't remember what JT65 is, but it's probably pretty close to that. So these tones are only a few hertz apart. Just capture the blue text there. One other interesting factoid with JT65, the payload is only 13 characters. So for that minute that it's transmitting, it's only sending 13 characters, and everything else is error correction information. We're going to get to error correction in a little bit. Mentioned Whisper briefly. Weak signal propagation reporter. This is not a two-way mode, it's a one-way mode. The way that it works is you send out a Whisper packet, or beacon you could call it, and it's picked up by stations in other parts of the world and put onto a computer website or onto a server so that you can tell what the propagation is between where you are and where that location is. It can be really handy for comparing antennas. So you can transmit on your tri-band beam for maybe 5-10 minutes and then switch to your wire antenna for 5 or 10 minutes, note the times, and see how they're being received. So you can compare antennas that way. But it does not support keyboard-to-keyboard operation because it's basically a one-way system. The newer modes, FST4, we talked about a little bit, and Q65, they're the newest ones in the family. And all of these modes are generally organized by purpose. So moon bounce has a mode that's good for it. Whisper we talked about. Meteor scatter we're going to get into when we get into the propagation chapter in 3 weeks. And then some modes are optimized for best long-distance communication. And I put this table together. It helped straighten out some of this for me. And I highlighted the portions in blue. We saw this as we were going through the slides, but FT8 takes 15 seconds for a single transmission. It's really designed for distance communications. FT4 was the faster version, really designed for contesting. JT65 was the original moon bounce that these others were based upon. It takes 60 seconds for a transmission, which seems horrible right now, but back when that's all that was available, we thought it was wonderful. It uses multi-tone AFSK, 65 tones, originally for moon bounce. Whisper we talked about, designed for weak signal beacon. Propagation reporting, does not support keyboard-to-keyboard communications. There's a mode designed for meteor scatter, which is a fascinating mode, actually bouncing signals off of meteors. We'll get to that in 3 weeks as well. Then these are the two newest modes, Q65, and its claim to fame is it can average receive cycles. So you can vote. If you hear something 2 or 3 times in a row, you pick the one where the majority wins, and it's probably going to be right. Then FST4, this is the one with all of those cool words, variable transmit receive periods, up to 30 minutes, 7 different tone spacings, designed for LF and HF. So that would be like the newest low frequency bands, the 630 meter band and 220 or 2200. So we're going to move on. I found this chart kind of helpful. That's why I put it together, is to compare and contrast those things. I didn't go through all of these, but it's there for you if you're interested. And then to another topic that's kind of complicated sounding, ODFM. In Kessler's video, when he talked about how this works, he said, well, you might want to just consider it as magic. Okay, but we'll get into a couple of things that relate to the pool questions. Stands for orthogonal frequency division multiplex, and it's used for digital modes. It's a modulation method that uses subcarriers. We kind of talked about subcarriers when we were talking about multiplexed signals in a previous lesson. So here they're showing the main signal and some subcarriers. It's a digital modulation tech using subcarriers at frequencies chosen to avoid inter-symbol interference. You notice how these are interleaved such that they don't collide with other things that are going on, I guess would be the simplest way to state it. If they did happen to get off frequency, they'd be interfering with these other symbols that were going on. So that's why they said it the way that they have, a digital modulation technique using subcarriers at frequencies chosen to avoid inter-symbol interference. And on to some questions. What technology is used for real-time tracking of balloons carrying amateur radio transmitters?
Charlie.
It is Charlie, APRS. What digital protocol is used by APRS?
Charlie.
Charlie again, amateur X25, AX25. What type of packet frame is used to transmit APRS beacon data?
Charlie.
Charlie.
Well, we're on a Charlie streak, that's correct, unnumbered information. So we don't care if the packets are out of order. That's why we can do that, makes it simpler. How do APRS stations relay data?
Delta.
Delta.
Okay, funny somebody didn't say Charlie. Delta by packet digipeaters. Those can be connected to the internet or not. What does the packet path wide 3-1 designate?
Charlie.
Charlie.
Back to Charlie. 3 digipeater hops were requested with 1 remaining. You normally won't have to spend too much time figuring that out. Which of the following HF digital modes can be used to transfer binary files?
Bravo. Bravo.
Bravo is correct. PACTOR. Which of these digital modes has the fastest data throughput under clear communications conditions?
Delta.
Delta, that's PACTOR 4. Which type of modulation is used by JT65?
Alpha. Alpha.
It is alpha, multi-tone AFSK. It actually uses 65 tones. Which of the following synchronizes WSJTX digital mode transmit receive timing?
Bravo. Bravo.
Bravo, synchronization of computer clocks within 1 second. Which of these digital modes does not support keyboard-to-keyboard operation?
Alpha.
Alpha, whisper, because it's propagation reporting only. Very sensitive mode. What is the length of an FT8 transmission cycle?
Charlie. Charlie.
15 seconds, correct. What is the bandwidth of an FT8 signal?
Bravo.
Bravo.
It's Bravo, 50 hertz. So if you consider a sideband space as being about 3,000 hertz, if you divide that by 50, that's how many FT8 conversations or exchanges you could have. You don't really do conversations in FT8, but that's how many you can fit in that space. With the CW, what we talked about earlier, since you're hearing it with your ear, you can't really get them so close because they start running together. But with FT8, you can literally just be 50 hertz apart and have a successful contact. You get tons and tons of signals into that 3 kilohertz space. So what does the 4 in FT4 refer?
Bravo.
Bravo.
4-tone, and then the fancy words continuous phase frequency shift keying, but the 4-tone, yep. How does Q65 differ from the other modes? JT65 is specified here.
Charlie.
Charlie, that's
Charlie.
the one where multiple receive cycles are averaged. They can figure out which one is correct. Which of these digital modes has the narrowest bandwidth?
Charlie.
Charlie, right? There are some that are narrower than that, but of the ones that are listed, FT8 is the narrowest. Which of the following is a characteristic of FST4?
Delta.
That's delta. It's got all of these fancy words, the four-tone Gaussian frequency shift, all of this kind of stuff. And orthogonal frequency division multiplexing is a technique used for which type of amateur communication?
Alpha.
Alpha, digital modes. And what describes orthogonal frequency division multiplex?
A digital mode using carriers.
Yes, right.
Delta.
Exactly. Delta. Yep. Very good. What is a common cause of overmodulation of AFSK signals?
Delta.
Delta, excessive transmit audio levels. It's a little too quick on the finger there, but you got it anyway. What parameter evaluates distortion of an AFSK signal caused by excessive input audio levels?
Delta.
Yep, intermodulation distortion. A lot of times your receiving software will actually give that to you as a number. What is considered an acceptable maximum intermodulation level for ASK?
Delta.
That is delta, yep. Yeah, remember the 3-second rule, or you won't get your cookie. All right, so now we're moving into something else called spread spectrum and error correction and detection. Some fascinating, fascinating stuff. Spread spectrum is something that you're probably not going to use, but in the amateur world, there are applications. You use it every day at home because it's how your Wi-Fi works, okay? So how does this work? Spreading a signal over a very wide bandwidth by rapidly varying frequency in a predefined sequence, called a spreading code. And there's two flavors. This is one flavor we'll talk about. And because we're sending that signal over many frequencies, the signal strength on any one frequency can be pretty low. In fact, if you lose one, that's okay too. So you can figure it out. So dilution of the signal across many frequencies make it sound like noise to a conventional receiver, maybe below the noise floor. So somebody can be communicating with spread spectrum, and if somebody were to tune there, they wouldn't even know you were there. It's resistant to interference because signals not using the spread spectrum algorithm are suppressed in the receiver because they don't match the spreading code. And the other issue is, of course, they're spread over such a large area, you wouldn't even notice that they're there because they're sent at a very low level. But this is the context of the pool. It says suppressed in the receiver. So all of the other signals, we've got a picture down here. I think I've got a bigger one. Yeah, bigger one here. So that this would be a normal signal. We'll call it a carrier, a CW signal, or even sideband. And here's the noise level. In order to hear our sideband signal, it's got to be above the noise level by, we saw, at least 10 dB. And it's consuming this amount of the spectrum, let's say, relatively speaking. With spread spectrum, it's sending that signal, it's spreading it across a much wider frequency range and can actually be below the noise level. So with that, all of our conventional signals, receivers will ignore anything that's going on with spread spectrum. And many systems can share frequencies by using different spreading codes, something called CDMA. That's how cellular works. You can have all kinds of conversations going on using exactly the same frequencies, and you only hear the person, the party to which you are speaking, as they say. Now there's two flavors that we're going to talk about. There's actually 4 flavors, but there's only 2 that are mentioned in the pool, only 2 that are legal for hams to use. There's frequency hopping, and as you might expect, that is just what it is. It's making the signal bounce around all over a given range, probably 10 to 100 times the width of a sideband channel, for example. So the frequency of the transmitted signal is changed by rapidly varying the frequency of the transmitted signal according to a pseudo-random sequence. To anybody that doesn't know that sequence, of course, your transmitter and the other party's receiver have to know what that sequence is. in order to accomplish the communications. So that's frequency hopping. That's the easiest one to visualize because you can see those frequencies bouncing around. The other one is a little bit harder to visualize. It's called direct sequence. It uses a high-speed binary bit stream to shift the phase of the RF carrier. And then, of course, the receiver has to reverse that. So these are the two flavors that are used in ham radio. And Wikipedia has an article, if you care to go further. The other types are called time hopping and chirp SS. These are described in Wikipedia, but they're not used in ham radio, not legal. So here's a picture of frequency hopping, and you can kind of see that things are hopping all over the place here. So this is frequency hopping spread spectrum in green. And then the other one is the phase shifted one. That's also occupying a similar distance, but it looks very different in a spectrum display. And then we'll move on to something called quadrature amplitude modulation, or QAM. I think there's two pool questions about this. Now remember when we were talking about phasor diagrams and vectors, where a value of signal would have both an element of magnitude and direction? Okay, well let's look at this diagram here. Happens to be for 4 QAM, which we'll get into. Now notice these dots here. When we were doing complex impedance, we'd go a certain number of spaces over on the x-axis, the real axis, a certain number of spaces up. In this case, it'd be inductive reactance to get to this point. So the magnitude is from the origin to the dot, and then the phase was the angle from this line, the x-axis, up to that point. So in this case, if we were doing a complex impedance, it would be, well, in Cartesian coordinates, it would be 2 plus J2. We'd have a 45-degree angle and then some value of magnitude here. So you can kind of get the concept. I'm trying to relate it to something we've talked about before. So in the case of quadrature amplitude modulation, we're concerned about a level, a distance from the origin, and an angle up. So here we've got 45 degrees, 135, so forth around the circle. So it uses a combination of amplitude and phase modulation. We're changing both the amplitude and the phase. So two types of modulation make it possible, amplitude and phase, to pack more data bits into each modulation symbol, resulting in more throughput. Remember how we assigned numbers to fingers when we were talking about symbol rates? Well, we're not using numbers and fingers, but we're doing different levels and angles. So QAM, quadrature amplitude modulation, is transmission of data by modulating the amplitude of two carriers of the same frequency, but 90 degrees out of phase. That should remind you of I and Q signals that we talked about a while back as well. QAM, now this is called a constellation diagram, because if you could imagine yourself looking off into space, well, here we've got these stars at certain locations. This is called a constellation diagram. Shows the possible phase and amplitude states for each symbol. So this symbol represents 2 bits, 0, 0, 0, 1, and so forth. So like I said, we talked about phasors in chapter 4, magnitude and direction. This is the same concept. All right, distance from the origin is the magnitude, like this. Angle from the x-axis represents the direction or phase angle. Can it get more complicated than that? Absolutely. All right, so here's 4 QAM, which we just discussed. What about 16 QAM? Wow, look at this one. So instead of 1 spot per quadrant, now we've got 4. So that's 16 altogether. So each one of these dots represents a different magnitude and direction. And you can see that we have the possibility of many more bits that we can encode just by picking. So that it can become more complex than that. There's also 64 QAM, and I won't even go there because your head probably hurts already. So where are some of these things used? So the quadratary amplitude modulation is can be found in mesh networks and the spread spectrum and various other places. So there's a book out called High-Speed Multimedia for Amateur Radio. And the concept of mesh networks, it's like having routers in your house, except they'll transmit and receive, and they're interconnected, and you can spread these around a city. So the concept of a mesh network is, let me see if I got a diagram here. I guess I've got one coming up. So it's an application used in amateur radio. You can use higher power than standard Wi-Fi. We can use 10 watts versus 1 watt maximum for a router in your house. Most routers in your house will probably only be 100 milliwatts rather than a watt. So you can get much more power. And of course, we can put them up on antennas on towers and cover an entire city. And there are some cities that have emergency networks set up using mesh networks that are there specifically in case everything else goes down in that city. Frequencies are shared with unlicensed wireless data services, or 2.4 and 5 gigahertz Wi-Fi. There are pieces of the ham bands that are in those Wi-Fi areas. How do we accomplish that? Well, we don't need super special equipment. We can use a standard wireless router, certain brands anyway, running custom firmware. So if you've got I think Linksys is one that's supported in certain models, you can get custom firmware that will allow you to run this amateur protocol on that router. Individual nodes form a mesh network, so you've got these spread around by using discovery and link establishment protocols. Remember, we talked about ALE, automatic link establishment. This isn't exactly the same implementation of that, but it's the same idea. So these nodes can listen to each other. A little bit more. There's no encryption. Messages cannot be encoded to obscure their meaning. We saw that before, unless you're talking to a spacecraft or a model plane. Frequencies used for mesh networks are shared with unlicensed wireless data services, which we saw. And then a little technical tidbit, nodes in a mesh network use the internet protocol. So on the internet that you go from your computer to a server someplace, that's usually TCP/IP, and it's the IP portion of that internet protocol that's the protocol used in mesh networks. Now there's something new. There's no pool questions on this, but it is something that's kind of taking radio by storm in some cases, called Meshtastic. There's a website here. Began in, and this is just background information, began in 2020. In its original use was communication off-grid, so no cellular or Wi-Fi. Now you could plop these Meshtastic nodes in different places and set up a network that you could pass message traffic over. Range of several miles, uses unlicensed radio bands. In ham radio applications, these systems can be combined with conventional ham systems for emergency communications and event coordination. So it kind of supplements some of the things that we're doing. You'll probably be hearing a lot more about that. This is something that's fairly new. Just wanted to mention it because you'll hear of it. Not related to our exam though. Error detection and correction. Okay, this is some fun stuff. What good is data if it's corrupted? So look at this poor guy here. There's a puzzle piece missing. He's not getting his full message. So RIDI and PSK31 have no error detection or correction. We saw previously that with ASCII, by adding parity, we could detect some kinds of errors, single bit errors. And now a new term here, cyclic redundancy check, or CRC, can detect multiple bit errors. And then there's something called automatic repeat request. how automatic repeat request accomplishes error correction. If errors are detected, a retransmission is requested. So kind of look at the words there. ARQ, automatic repeat request. So if you received the packet correctly, you could respond with an acknowledgement or an ACK. If you didn't receive the packet correctly, you would probably want to send a NAC, not acknowledged, which would cause the packet to be retransmitted. We have a concept called forward error correction. Now, it's possible to add a lot of redundant data up front to correct errors. I mentioned with JT65, we only had 13 bits in the payload, and we were taking a whole minute to send it. All the rest of that was error correction, forward error correction data. So it's possible to add redundant data up front to correct for errors. One way, this isn't how they do it, but let's say that you sent it 3 times. Well, if 2 out of the 3 were the same, you could probably assume that that was the correct data. The one that was the oddball, you would ignore. Implemented by transmitting extra data that may be used to detect and correct transmission errors. There's all kinds. You've probably heard of some of these things: Reed-Solomon, Hamming, BCH, Golay. They're all types of codes that can be embedded in a message to help you detect and correct errors. However, if the data rate exceeds a certain threshold, then it just has to give up. Kessler mentioned Viterbi encoding. The engineer in him wanted to come out again. And he said that this was a means that they were using in deep space spacecraft to decode messages. It restricts the number of symbols sent over the air to a subset of the original data, and then the decoder algorithm can then present the most likely data to the decoder sent by the encoder. So here's some diagrams. Forward error correction. A packet will typically have a header, and then this is my message for you, the payload, and then the checksum. This is all information that it adds up all of the numerical values, and then tries to tell if it was correct. So the sending computer uses the desired message text to create a checksum using an algorithm such as CRC, cyclic redundancy check, which you don't need to know about. Entire package of bits is sent over the air. And then on the receive side, it uses that checksum information to determine if an error exists, and if possible, it uses the redundant information to reconstruct the data to recover it. So if it's a mismatch, it attempts to reconstruct. The automatic repeat request, in this case, if it gets bad data, it'll ask for a resend. If mismatch, request a resend. And I put together a little diagram here that illustrates this. So we've got a sender and a receiver. The sender will send data to the receiver. The receiver will say, okay, the checksum matches, that data is okay, so it can send an acknowledgement or an ACK. When I send more data, the next packet, uh-oh, that's not okay. So what do we do now? We're going to send a NAC, not okay, in an automatic repeat request. Send it to me again. So it's going to resend the data. This time, it was received okay, and it'll send an ACK. So we have just gone through the entire sequence. That's how it works. Some questions, and then we'll probably be taking a break here. Why are received spread spectrum signals resistant to interference? Alpha, signals not using the spread spectrum algorithm are suppressed in the receiver. Which describes easy for me to say, which describes spread spectrum frequency hopping?
Delta.
Delta, it's the one where things are hopping around, varying the frequency of a transmitted signal according to a pseudo-random sequence. So this is the easy one to identify. When we get to the other one, By contrast, you should be able to pick out the answer. What spread spectrum communication technique uses high-speed binary bit stream to shift the phase of an RF carrier?
Bravo.
Bravo, that's the other one. Yeah, we have frequency hopping and direct sequence. So if it's not the frequency hopping one, it's the other one. What is quadrature amplitude modulation, or QAM?
Bravo.
It is
Bravo.
Bravo. Transmission of data by modulating the amplitude of two carriers of the same frequency but 90 degrees out of phase. That results in both amplitude and phase modulation for each data point. What is described by the constellation diagram of a QAM or QPSK signal?
Bravo.
Bravo, it's the phase and amplitude states for each symbol. Of course, there can be, we saw up to 64 in one of my diagrams. Which of the following cannot be transmitted over, or 16 is what I diagrammed. Which of the following cannot be transmitted over an amateur radio mesh network?
Delta.
Charlie, yep, no secret agent man stuff. Messages encoded to obscure their meaning. Which of the following frequencies can be used for amateur radio mesh networks?
Bravo.
Bravo, frequencies shared with various unlicensed wireless data services, the 2 and 5 gigahertz Wi-Fi bands. What type of equipment is commonly used to implement an amateur radio mesh network?
Charlie.
Charlie, wireless router running custom firmware. What type of addresses do nodes have in a mesh network?
Charlie.
Charlie, that's the internet protocol. What technique do individual nodes use to form a mesh network?
Charlie.
It is
Charlie.
Charlie, discovery and link establishment protocols, kind of related to the ALE concept we talked about previously. How does ARQ accomplish error correction? It's helpful to remember what ARQ means, automatic repeat request.
Delta.
You heard delta in there. If errors are detected, a retransmission is requested. And then we're going to move on to amateur television. So it took you a little bit more than an hour before you got your break. So you have a well-deserved 5-minute break at this time. Enjoy. Okay, we're back. I hope everybody's rested and ready for something totally different. Amateur televisions. This goes back to, okay, the analog version of amateur television is just like the early TV channels. Took up 6 megahertz of bandwidth, and some people call ATV ancient TV rather than analog television. So there's a lot of pull questions on this, so we still need to talk about it, but not used very much in amateur radio except in large cities. I think St. Louis has got a group. There might be some other big cities where there's some folks that still enjoy doing this sort of thing, but it's a very small niche mode of amateur radio. But we're covering it because of the pool questions. So where did all this come from? Well, back with commercial television, there was something called the National Television Systems Committee. This goes back to 1941. Believe it or not, that's before I was even born. Color was added in '53 with another standard. What we're calling amateur television, or fast scan, as used in the current exam pool, uses these NTSC standards. And DATV, digital amateur TV, is in our future, and there's work going on in that area. We'll mention just a couple things about that at the end. Oh, and I think I had a link there. Yeah, there's an article. Now, RSGB, that doesn't stand for Red, Green, Blue. That's the Radio Society of Great Britain, but they have a really good article about digital TV, but we're getting to that later. So what do we need to know? Well, here's a system. We've got a TV set. This is like before digital TV, back when we had channels 2 through whatever they were. We had a special ATV, amateur TV transceiver. Why is that? Well, it had to be able to transmit a 6 megahertz bandwidth transmit signal. So obviously this only happened on UHF and above. TV camera, microphone. And it was really hard to get a clear picture, so you'd usually see the specialized transceiver for this purpose, and then probably a power amplifier and a gate antenna. Analog TV standards used. Allows commercial analog TV receivers to be used for fast scan TV operations on the 70 centimeter band, transmitting on channels shared with cable TV. So it is possible, if you've got an old analog style non-digital TV set, you can tune to some of the cable channels to actually pick up the frequencies that we would use in ham radio. So a little preliminary information. What we're actually going to be doing is sweeping a beam across a screen. We'll start at one end, go down, and then we'll blank it very quickly, move back over to the beginning, down, down, down. This starts in the upper left-hand corner. This next scan will start a little bit later. And when you combine these two together, you'll get one complete picture information. When you get all the way to the bottom, you've got to move your electron beam back up to the top. And that's what these things are doing. So Kastler had some wonderful diagrams that I've stolen here. So we want to take a picture of this flower. So we're going to just look at one line described here. Then we've got signals ranging from white to black. So you notice in the range of white to black, blue is kind of in the middle. So as we're scanning that particular line of the picture, here's the signal. And then we've got some stuff, the petals of the flower jumping up and down. And then it gets dark, the signal goes toward black. Then the yellow goes up. And you can see that this waveform, as we're scanning this particular line of the video, this is the signal that's being created. So the way that the math works out here, we're going to have 262.5 scans for each field. I mentioned that we start out upper left and then we start out here in the middle to form a full picture. So 262.5 scans for each field. That adds up to 525 scans for the complete frame. So a field is half the picture, and a frame is the two halves put together. Multiple scans. So here's one. Here's the other. You combine the two together, you get the full flower. So we have 30 odd fields per second, 30 even fields per second. So we have 60 total fields per second, 30 frames per second. You can kind of see how that works out. So a summary of what we're dealing here with NTSC fast scan. Oh, Gary had a humorous thing that I wanted to mention as well. In fact, he might say it.
Well, that was back in the day when I was a broadcast engineer for TV stations. NTSC, we always said, stood for never twice the same color.
Yeah. Yep. It was difficult. I mean, with really careful calibration, you get really good pictures, but it was tough. All right, we saw that standard. And it uses an interlaced scanning pattern, which we demonstrated, generated by scanning the odd numbered lines in one field and the even numbered lines in the next. 525 horizontal lines make up a fast scan television frame, 262 plus 262 and a half each. 525, remember that. 30 frames, complete picture per second. Now, what does a waveform look like? There's an organization that standardized all of this. I'm just looking for their name here.
Institute of Radio Engineers,
IRE. Well, I got it on the slide.
which later became the IEEE.
Some wonderful history there. So they had to, in order to keep the video from tearing and getting out of sync, they used something called sync pulses before and after the active video. So here's the active video, just in microseconds level. They had what was called a white level and black level. White level was considered, instead of using voltages, they used a value that they called IRE levels. So here's white and here's black. And you can see that the sync pulses are actually below black. So sometimes these were referred to as blacker than black. So here's a repeat of some of the things we talked about: field rate, frame rate, horizontal lines. There was I said that the channel bandwidth was 6 megahertz. That's why this only happens at UHF and above. And then there's a sound subcarrier at 4.5 megahertz, because you want sound with your pictures. And the line rate, if you combined all of this together, was 15,750 hertz. And if you were young and had very good hearing around one of these television sets, you could actually hear this super high frequency. And I would think that this would drive dogs nuts, but I never knew that to be the case. Now color came along, and it was a little different. The Standards Committee and at the FCC wanted to make sure that anything that was transmitted in color had to be backwards compatible with black and white. So they had to make some minor adjustments to some of these numbers to make the color information fit the math. So you can see that these are a little bit different. We had 15,750 before. We had a 60 hertz frame rate or field rate, 59.94. So you can see that these numbers are slightly modified. And then there was a color subcarrier that was used to synchronize the color information, the sound subcarrier we saw before, and the total channel bandwidth. So here's what the display would look like if we were dealing with color. So we saw the signal here. It was black and white. Also, we could consider that the luminance information. The chroma, or the color, is here. Notice that the luma carrier is over here. We use something called vestigial sideband. So the video is sent as an AM signal. Vestigial sideband means that we cut off part of the lower sideband. It's a vestige of the sideband that was there, a vestigial sideband. Then there's a guard band in between television channels so that they don't bleed into each other. The audio sits on a carrier, a subcarrier that's 4.5 megahertz above the video carrier. We see that over here. That's sent as a frequency modulated signal. So this just kind of gives you a perspective of how all of this information is crammed into one signal, color signal, via the RS-170A color spec. Just interesting background at this point. Why did they use AM signals? Because it's easy to detect. All you need is a diode. So the couple of differences with the color scan lines. They have a chroma burst here. They've got to do some things to get the color information in there. Frequency of the color. A bunch of numbers here aren't really important. Just one thing I'll mention in passing. You very much want the signal to be in sync. You don't want to have a rolling and tearing picture, so that actually send this signal upside down so that the maximum amplitude being sent by the transmitter were the sync pulses. Because that was really important. You wanted the picture to be stable. And then of course that had to be reversed on the receive side. All right, a couple of questions on vestigial sideband. It's amplitude modulation in which one complete sideband and a portion of the other are transmitted. We showed that in a previous diagram, but here it is again. Here's the video carrier, the full upper sideband, and then the lower sideband is cut off. Use of vestigial sideband with analog fast scan TV. It reduces the bandwidth while allowing for simple video detector circuitry. Just a simple diode. So just two concepts relating to vestigial sideband, why we use it and what it is. All right, I think we talked about all of this before. Leave it up there for just a bit. So a common ham frequency where the folks use this is at 1255 megahertz. Can't do this on your HF transceiver. Some more terminology. Luminance we saw was the black and white part. Chrominance is hue and saturation. Some conceptual pictures, again courtesy of Mr. Kessler. Hue, saturation, luminance. Red, green, and blue are converted into hue, saturation, and luminance. Just some more terminology here. Now we get into how do we actually get the color information superimposed on the luminance information, or the black and white portion. So if there's 15,750 scan lines per second, results in a spectrum that kind of looks like a comb. And a black and white TV signal doesn't do anything with the information in between. So wouldn't that be a wonderful place to put the color information? Guess what? That's what we do. So the luminance is the black and white information. The chrominance, the color, gets slotted in between. So this is just a conceptual picture of how that's done. And a big marketing feature back in when color was first out, they used something called the comb filter to make sure that these didn't interfere with each other. And that was a huge marketing thing. The folks that were selling color TVs were bragging about their comb filters. All right, so in the amateur world, how are we going to transmit audio with the video? Well, the NTSC standard, which we don't have to follow because we're not sending commercial TV out to the world, we're just communicating amongst hams. NTSC uses an FM subcarrier above the video carrier. Hams, however, have used and do use frequency modulated subcarrier, which is the NTSC method. They can use a separate VHF, UHF audio link. They can frequency modulate the video carrier. That sounds kind of hairy. Or just narrate over a cell phone. All that works. So can you hear me now? Now let's move on to, well, just a review of the system. Special transceiver, amplifier, gain antenna, TV camera, old style TV set, and a few questions. What technique allows commercial analog TV receivers to be used for fast scan TV operations on the 70 centimeter band.
Alpha.
It is alpha. Transmit on channels shared with cable TV. So if you ever want to get into this, don't throw away your old TV set or find one at a yard sale. How many horizontal lines make up a fast scan NTSC television frame?
Charlie.
Charlie.
This is Charlie, 525. How is an interlaced scanning pattern generated in a fast scan television system?
Delta.
Delta.
Yep, scan odd and even separately and combine them. Which of the following describes the use of vestigial sideband in analog fast scan TV?
Charlie.
Charlie is correct. Vestigial sideband reduces the bandwidth while increasing the fidelity of low frequency video components. We didn't talk about increasing the fidelity, but we did talk about reducing the bandwidth. What is vestigial sideband modulation? How do you do it?
Alpha.
Alpha.
It is alpha, amplitude modulation, in which one complete sideband and a portion of the other are transmitted. All right, so that's the analog piece. Now we're going to talk about slow scan. Now analog is special, or the fast scan analog is kind of special, it requires special equipment. Not very many hams are doing it. However, slow scan is something that you are able to do if you've got nothing more than a standard HF transceiver, believe it or not. So there's two flavors of slow scan. There's analog and digital. So the International Space Station transmits images using slow scan. Here's an image. And there's a gallery here. I looked at that. There's not a lot there right now, but the people have put pictures out there. And there's a website, ariss.org, talks about what they're doing. So slow scan, not actually television. It's not moving pictures. It's just single images that are being sent, but it's still called television, but it's not moving pictures. So it can use sound card-based software. In other words, it's a program you'd put on your computer, and then you would connect you'd be transmitting on single sideband, on HF or FM on VHF. So just the equipment that you already have in terms of a transceiver. Approximate bandwidth, notice that anything digital that goes on is always going to be in the space of a single sideband spectrum, 3 kilohertz. Now, because we're sending this out just like we would using the microphone connection to receive audio, we're going to be using tone frequencies. So there's about 3 different pool questions that asks, how are you going to do something? And the answer is almost always tone frequency. So if you're sending data or changing things or whatever, they're all going to be happening as different tone frequencies. So varying the tone frequencies are used for brightness, video, new picture line signals, specific tones. Has to fit in a sideband space. There's no interlace, 1 frame per picture. When we were sending one half of the picture and then the other, that was called interlaced video. There's no interlaced here. NASA used a form of single side or slow scan TV for the Apollo program. Of course, it's used on the International Space Station today. The equipment, it might look similar, but there's a lot of differences. First of all, because we're doing still pictures, we can get something from a scanner. We can use a camera still photo, digital picture on your cell phone. If you're using video, you'd have to have a frame grabber to get a single image. And go into the computer, the software. sound card, either in the radio or externally, and then to an HF radio. So you've already got the HF radio. You probably already have the sound card, either in the radio or in your computer. So all you need to do is get the video stuff, and you've got a cell phone, right? So you've got just about everything you need to do this right now. So what are the common numbers that are involved here? You don't need to know any of these, but you'll notice that the numbers are radically different than we saw with the analog TV, the fast scan. Frame time, 8 seconds, lines per frame. So it takes a while to get this image sent. There's different standards that are used, and these are all common ones: Scotty, Martin, and Robot. Don't know a lot of details here, but we know what the mode is, and these are the kinds of things that they send. How long does it take to send an image? Well, Scotty S1 takes 110 seconds to send. It's 256 lines. Just a little contrast between some of these common slow scan TV modes. So how color information is sent? Color lines are sent sequentially. Some more things to grab. Aspect of an analog slow scan television signal that encodes the brightness information of the picture. Surprise, surprise, tone frequency. Okay. Now there's something that happens when you well, let me read it and then I'll come back and explain. The vertical interval signaling, or VIS code sent as part of an SSTV transmission, is used to identify the SSTV mode being used. Now the vertical interval signaling, that happens as you're going from the bottom to the top of the picture. So we want to send identify the mode being used. And we saw earlier, okay, we've got Robot, Martin, Scotty, and then the different variations within. So that information gets sent during this period. The vertical interval signaling period identifies the type of transmission being used. Guess what? Specific tone frequencies, again, are used to signal the SSTV receiving software to begin a new picture line. Here's an article if you want to dig deeper. Some cautions. It's a 100% duty cycle. Talking slow scan TV. So if your transceiver can't handle 100 watts continuously for a period of time, excuse me, you may need to reduce power. Excuse me. As with other digital modes, no ALC or speech processing. So we don't want to distort the transmitted signal in any way. ALC is really something that you use for single sideband. You don't want to have any ALC action when sending digital signals, in SSTV in particular, because it distorts the transmitted signal. No noise blanker or DSP, just as clean as you can make it. And these are the common frequencies that you would see this being used on HF. So if you want to tune there, you might hear some really weird things going on these frequencies, and if you do, it's probably slow scan TV. Some people will use their QSL card as their identifier, because you have to identify your transmission just like you do with any other mode in ham radio. So station ID via picture is okay. Voice is fine as well. And that's all we're going to be talking about regarding slow scan TV. There's something called digital slow scan TV. Everything we talked about so far is analog. So with digital, it's based on a standard called DRM, and that's a European word. Digital Radio Mondial is how I pronounce it, but I went out on the internet and there's about 3 or 4 different ways of pronouncing that, but DRM, that's easy.
Mondial is French for international.
International, okay, thank you. Yeah, having never been in Europe myself, I have to depend on Gary for all of the translations. DRM acceptable bandwidth is 3 kilohertz, just like it is for everything else that we do on HF. for voice or slow scan TV. Same for digital. An SSB receiver can be used to receive and decode SSTV using DRM protocol, DRM software. So again, you can do this with just standard, listen to my voice, standard ham equipment. There's software available, free, EasyPal. Here's a site where you can download it. This might be kind of fun to do. See what's going on the International Space Station, frequency where it's most often found, and then some links here if you want to dig a little bit deeper. And then there's something called digital television. That's not, we're moving away from slow scan now to digital television. And there's something called DVB-T, Digital Video Broadcasting Terrestrial. I thought, well, why the word terrestrial? Well, to me, that's because it's not coming via satellite. That's ground-based transmissions. European standard, published in '97, first used in Singapore, so it's something that is actually being used. Were they doing any of this while you were over there, Gary?
Oh, absolutely. In fact, if you look at the TV monitor that is behind you that is displaying the slide, I bought that TV in Germany, and it does have a DVB-T tuner inside and could be used to receive those transmissions.
Yep. Very good. So it got started over there. I don't think it's really caught on over here, though, at all. It has been adopted by amateurs. So the equipment is out there and available, just like the monitor behind us. Modulation used for amateur television, DVB-T, is QAM. Remember we talked about QAM, and you were probably wondering, why in the world would you ever need something that goofy? Well, here's an application. Quadrature amplitude modulation, quadrature phase shift keying. In digital television, a coding rate, now this is just a technical tidbit. We're not going to even attempt to explain what this means, just recognize the words. In digital television, a coding rate of 3/4 means 25% of the data sent is forward error correction data. So just accept this as a fact. If you really want to understand what it means, you'll have to Google and dig into the specs. But probably not too many of you are going to be interested in that. Now, when it
that
works,
also goes back to DVB-S. A lot of television was distributed in Europe via direct satellite, and they would use forward error correction a lot to get their signals down. So this is, a complete standard.
Yep, very good. Satellite and terrestrial. So this is a picture of a happy TV when everything works right. And on to some exam questions. And we're almost done. How is color information sent in analog SSTV?
Alpha.
Yep, color lines are sent sequentially. What aspect of an analog slow scan television signal encodes the brightness of the picture?
Alpha.
Yep, our friend tone frequency. You'll see that probably twice more. What is the function of the vertical interval signaling code sent as part of an SSTV transmission?
Bravo.
Bravo.
Bravo. Identify the SSTV mode being used. What signals SSTV receiving software to begin a new picture line?
Alpha.
Tone frequencies again, specific tone frequencies. Which of the following is an acceptable bandwidth for digital voice or slow scan TV transmissions made on the HF amateur bands?
Alpha.
Alpha.
Yep, the space of a sideband channel. What kind of receiver can be used to receive and decode SSTV using DRM?
Delta.
Delta, standard SSB transceiver. In digital television, what does a coding rate of 3/4 mean?
Alpha.
Alpha.
25 of the data sent is forward error correction data. And what types of modulation are used for amateur television DVB-T signals?
Bravo.
Bravo.
Yep, those constellation diagram pictures that we showed you. And you have earned an award for getting to the end of this chapter. Okay, we covered a lot of stuff, but I hope it was a little bit easier than some of the other things that we've covered in past lessons. So at this time, we can move on to Gary's favorite part of the night, class chat.
Any comments or questions?
Can't hear
Com-
Gary.
Comments or questions?
Can't hear you.
There
You
we
said-
go.
Is your mic on?
Yeah, it is now.
Oh, okay. Yeah, comments or questions?
All right, well, for next week, it's my magnum opus, Antennas and Feed Lines, Part 1. We'll go over the first 2 sections in Chapter 9 next week.
And I get a break for 2 weeks, so hopefully
Yeah.
my voice will be back.
I'll lose mine next week. So, yeah.
Exactly. Yep.
Thank you all.
All right, well,
You
thank
bet.
you for being with us. Thanks to all on YouTube. Very active chat session tonight. Appreciate that. And we'll see you next Tuesday. Until then, 73, y'all.
Three.
Yep. Take care.
Thank you.
Gary.
Gary.
Thank you.
Oh, somebody had a